has caused us to adopt a new perspective on black hole thermodynamics, on gravitational thermodynamics. And what I'd like to do in this series of lectures is give you an idea of what the subject is about, what the findings are that we've discovered in this and other people as well, and maybe close off the last one with some ideas of future directions for research. So to start this, actually just before that, this is a recent review on the subject that appeared in Classical and Quantum Gravity earlier this year that I did with David Kubasnak, who's been a long-time collaborator of mine in this area, and May Teo, who was a master's student at Perimeter. She's now a PhD student at Stanford. So if you want to get a good overview of the subject, it's here. I have a short book out published by Springer on the whole issue of black hole thermodynamics and the information problem and firewalls. I'll say a little bit about this during this session, but the focus of the whole series will not be on the information problem. So I thought I'd start off to orient everybody with a brief history of black holes and what they are. And it was learned recently that the very first person to come up with the idea that there could be such a thing was the Reverend John Michell in the year 1783. And apart from being a clergyman, he liked to do he had a scientific hobby, which is by and large the way science was done back then. And amongst other things, he helped with the first measurement of the mass of the Earth. But in his course of his various doings, he conceived that there could be stars that were very, very heavy. And he asked the question, what if there were a star that was so heavy its escape velocity was larger than the speed of light? Now back then, there was reason to think that light perhaps was a particle and that it felt gravity the way everything else did. So just the way as I toss this thing up, it accelerates this way, slowing it down, reaching a maximum and coming back. If I went outside and I had strong enough muscles, I could throw it and I could give it enough initial velocity it could escape the Earth. So his idea was, well, what if there was an object, a star, so heavy that its escape velocity was faster than light? Well, then he realized, well, it would have to be dark, because any light shining off the star would be pulled back into the star. And you could easily figure out the size such an object had to be relative to its mass, and the answer is given by twice Newton's constant over c squared times the mass of the object. Just take the kinetic energy plus the potential, set it to 0, and then make the escape velocity the speed of light, and that's the answer you get. This answer, of course, is now well known to be the Schwarzschild radius of a black hole, coincidentally enough, but back then that was not known. So this remained a bit of a curiosity, but then it got suppressed due primarily to the work of Laplace, who 13 years later made a very convincing case in this book that light did not have a mass, it was not a particle, it had wave-like properties, and so people forgot about what the Reverend John did. And in fact, it was only rediscovered about 25 years ago, to my knowledge, in the common scientific parlance. Probably a few people knew about it all along. But I promote this idea to let people know black holes go way, way back. Of course, they were called dark stars back then, not black holes. So they reemerge once the general theory of relativity is presented in 1950, 102 years ago, 102 years ago this month, actually. And as I'm sure most people here have some familiarity with, Einstein proposed that gravity was really intrinsically connected to the warpage or bending of space and time. And what we perceive as a gravitational force that causes this object to fall, that's the way we would look at it in Newtonian language. In this way of thinking, this object is simply following a geodesic in response to the curvature of space and time that the Earth generates by virtue of its mass. And so his idea was, he came up with this expression that I'm expecting most people, if not everyone in this room, is familiar with, the Einstein tensor. And he set it equal to the stress energy of matter multiplied by 8 pi times Newton's constant g. This g is not that g, but the same notation is used. And he was able to find that it reduced to Newton's theory when the speed of light was very large compared to the other speeds of particles in the theory. But it came to this man shortly afterward, Karl Schwarzschild, who was an astronomer but commissioned to be a lieutenant in the First World War on the German side. And he actually got injured and went to a hospital, and then he got sick and he died. But during that period he was hospitalized, he found an exact solution to this set of equations that we now name after him. We call it the Schwarzschild solution. And he was very good at solving differential equations, and he figured out a way to do it. He didn't do it using the coordinates we would use today, but it's definitely the same solution. And he found that this object had rather unusual properties, or rather this solution had unusual properties. The idea was that if you had some spherical object, this would be the curvature of space outside the object. But if the object had this size, it developed what we now call an event horizon. Back then, they didn't know what to call it. And the metric, as I guess you know, is written this way today, putting in the factors of the speed of light, c, and Newton's constant, g. And so it looks like this. If the mass is 0, then we simply get the metric of Minkowski flat space that had been developed about 8 to 10 years ago by Minkowski based on Einstein's theory of special relativity. So in this sense, general relativity warps space-time by making the measurements of time and distance functions of your location in the space. And that's how we describe curvature. So, in 1919, Eddington actually decided you could check one of the predictions of this theory, namely that light would be bent in a gravitational field. For example, a light ray from a distant star, if you have a star here and a light ray comes by, Newton's theory says it will just go straight past. But Einstein's theory says the sun warps space, so it will be curved and do this. So if you have a pair of stars, the light going past them will tend to curve together, and the stars, instead of looking like this, will appear to be like that. And so you can look at how light bends due to the sun if you look at the sun during an eclipse. And there was one in 1919, and he went out to check it, and sure enough, the light was bent. And the results of this experiment were announced in newspapers all over the world, and it's after this observation of Eddington that Einstein's name became a household word. Everybody heard of him after that. So, in the 1930s, again, relativity became a curiosity. It was a very difficult theory to test on the order of 90 to 100 years ago. Chandrasekhar did some calculations not directly connected to general relativity, but indirectly connected. He looked at how heavy stars could get as they burned up their nuclear fuel. In fact, it wasn't really clear how stars shone back then, but this was one of the instrumental aspects of developing that theory. And he established that a white dwarf could have a maximum mass of 1.44 times the mass of the sun, and if it were any heavier at the same radius, it would implode and perhaps become one of these strange objects. Well, could that happen? Well, Oppenheimer and Schneider did a calculation in 1939 that suggested, yes, in principle it could. if you started off with a ball of matter, let's say it was pressureless dust, it would implode under its own weight, and it would fall through that strange r equals 2gm over c squared surface that was known in the Schwarzschild solution. And this might have been studied more, except 1939 is when the Second World War began, and basically everybody in physics turned their attention to helping the war effort, and hardly anybody worked on general relativity. Some mathematicians did. Einstein kept trying to unify it with gravity and electromagnetism. These two results were connected by Tolman, Oppenheimer, and Volkoff to find the maximum mass of a neutron star. And they found that above this limit, nothing could stop gravitational collapse, and it should form into a black hole with a singularity inside. In other words, the field equations suggest that the entire structure of space will get more and more warped, more and more curved, until the curvature becomes infinite at the center of the collapsing object. But that means there's no space and no time at the center of the collapsing object, and the laws of physics break down. Now that was pretty strange, and people didn't really know what to do with it. There was some general thought that maybe this is just a very special case. Nothing is exactly spherical. If you have departures from spherical symmetry, this won't happen. Until these two guys came along, Roger Penrose and Stephen Hawking, and they showed, using a set of theorems in the mid-1960s, that singularities were generic. They were not the exception to the rule. They were the rule. Under very general circumstances, such as energy being positive, they were able to develop criteria for what meant that stress energy tensor, what it meant for that stress energy tensor TAB to be positive, to correspond to positive energy, and they showed, using that criterion and some other basic arguments, that matter generically will collapse to form a singularity, which meant the predictive power of general relativity ultimately breaks down. There are no laws of physics at such places, or rather, we don't know how to make them. So Penrose came up with this conjecture that these strange singularities, whatever they are cloaked by an event horizon. In other words, he conjectured that whenever one occurred, it would always be shielded from distant observers by an event horizon. And this is still a conjecture. In fact, there are certain ways of violating it, and people still work on that today. But then there's a debate about how serious such violations actually are. So the words black hole come about in 1967 when Wheeler, being aware of these theorems, coins this term, and he claims this is perhaps the greatest crisis in physics, a theory that predicts its own demise or breakdown. So people then began to study these objects somewhat more carefully, and what came along after that were things called the Nohair theorems, which basically stated that although an arbitrary distribution of matter will collapse to form one of these dark stars, or now black holes, the black hole itself is not characterized by anything in the structure of that matter except its total mass, its angular momentum, and any other electric charge or some other charge that it might have. In other words, a black hole was an extraordinarily simple object. A sun, if the sun collapsed to a black hole, that's a complicated object. It's got 10 to the 57 protons, it has sunspots, it has solar flares, it has all kinds of structure. All of that structure disappears when the object collapses into a black hole. And as far as the outside world is concerned, all that characterizes a black hole are its mass, its charge, and its angular momentum. So this is hair, this is possible, this is not possible for a black hole to give you the idea. And there are many theorems connected with this in general relativity that, curiously enough, today we are finding loopholes in the theorems that allow them to be violated. In particular, if you couple gravity to what are called scalar fields, then you actually can violate these theorems. But at the time, that was not considered. So, when I was probably the oldest person in the room, but certainly when I was a beginning grad student in undergrad, I was told black holes were still probably fictional. They probably didn't exist. They're very strange objects. Something in astrophysics is going to collapse to some maximally dense, minimally sized object, and, you know, they're just mathematical things. But in fact, now today, I think nobody believes that to be the case, and we believe there are genuine black holes way out there in space. The first step along this way came when Jocelyn Burnell, a grad student of Tony Hewish, discovered this periodic oscillation of something in the sky, highly regular. They called it, it was called a pulsar, and they gave it the name LGM1 for Little Green Men 1. There was some thought that maybe aliens were trying to send a signal to us. Nowadays, we know that's not true. It's caused because the neutron star is a highly dense object made of neutrons with a magnetic field attached to it that, as the neutron star spins around, sends a repeated pulse that we can detect if the angular position is right relative to us. But it renewed interest in gravitational collapse. It meant these crazy objects that Chandrasekhar and Tolman, Oppenheimer, and Volkov looked at actually were out there. And since then, we have seen what we now believe to be black holes. Of course, if you argue in strict orthodox terms, you actually can only find a black hole by the process of elimination. You can never be 100% sure of what it is. You can only rule out what it is not. But we do know there are very dense objects with all the properties we would expect a black hole to have. And so theorists, and most people being who they are, just want to call these things black holes, and that's what I'm going to do. We've seen them in binary systems, a black hole orbiting another object. We've seen them, we've now found that at the center of most galaxies, if not all, they all have supergigantic black holes at their cores. Our own galaxies is about 4 million solar masses. Again, when I was a student, I took an astronomy course from a guy named Bill Harris, and this came out in the newspaper. I was a third-year student, a discovery, what was the name of the galaxy, MG, some catalog name, and a supermassive black hole, and I brought it in, and I say, what do you think of that? Isn't this cool? And he said to me, Caltech has a good press office. So that expresses the skepticism people had at the time, but we found lots and lots of these things, and people now make their careers studying and finding these things. Gravitational lensing. Einstein realized that this was a theoretical possibility, but he also felt it was such a weak effect, the idea that a massive object bends light, that the effect Eddington saw was so small you'd never actually be able to see it in practical terms. Today, astronomers use this all over the place to find dark matter. We have lots and lots and lots of examples of galaxies being lensed by other heavier objects that are in their foreground, and this has now become a tool of research as opposed to a theoretical curiosity. LIGO. How many people here have heard of LIGO? Everybody, right? So this is, I think, one of the, this and the discovery of the Higgs, I think, are the two major scientific discoveries of the 21st century, although I might include the CRISPR gene splicing mechanism as a third place, but I don't want to, in physics for sure, that we have now seen both the Higgs boson and gravity waves. And gravity waves, When I was a student, oh, we're going to see them in the next decade. When I was a grad student, oh, we're going to see them in the next decade. When I was a young professor, we're definitely going to see them in the next decade. And on, but now we did. We finally did, and it is I think, a remarkable scientific achievement of many people. My personal opinion is this is the future of the subject to a very large extent. And it will provide, I hope, good scientific research for both observationalists, experimentalists, and theorists for decades to come. It really, I think, will make general relativity a truly experimental and observational science in a way it has never been in the past. So we've seen these things, and so far everything works. And curiously enough, theorists being who they are, now that we've had the best evidence we've ever had that black holes crash together and emit gravity waves, there's all kinds of theorists that are trying to think of ways that these things could not be black holes and still produce gravity waves. Which I guess in the spirit of scientific falsification we should do, but it's a bit ironic. And then finally, what's up and coming, in fact I think it's running now, is the Event Horizon Telescope, this project that you could actually image a black hole by looking at its silhouette of the light coming behind it. And due to gravitational lensing in the curvature of space, if you have a black hole, the light from behind it will create a certain image that's contingent on what we call the photon sphere of the black hole. So the idea is if you're looking this way, if a light ray's way out here, it'll be bent a bit, but it will reach your eyes or the observational device. But if it gets too close, it'll get sucked into the black hole. So there's a boundary between these two regions called the photon sphere. And of course, black holes don't exist in isolation. There are other massive objects around them that theoretically can distort and warp their shape. And so by imaging a black hole, we can learn about about how black holes are tidally distorted, and how they are tidally distorted does depend on whether general relativity is correct or not. And we might say, well, what do you mean? We know it's correct. We've got all these experiments. Yes, but with the exception of LIGO, perhaps, pretty much every experiment is in a weak gravitational field. So LIGO and the Event Horizon Telescope now offer us the ability to look at the behavior of gravity when gravity is not weak. And this is the first time in history where we actually can do this in a very systematic way. Okay, if you want to ask questions, please. I've talked a lot. Any questions so far? All of this is review and orientation. Here's a few pictures. Here's a picture of a black hole in a binary system. These are the actual astronomy pictures. What's believed to be going on is this star is getting, you can see the star getting distorted here by some dark thing in the middle of it. And what is believed to be going on is there's a black hole here of about 10 kilometers in radius that's draining gas off the star into what we now call an accretion disk, and this crud from the star rotates around emitting light, but as the particles get too close they can crash into each other and form a pair of what are called jets, high energy streams of charged particles. Black holes are active at the centers of galaxies, and here are some pictures that are connected with that astronomers interpret. This is the one I think is the most interesting, is this black hole called Sagittarius A, where that star is, Sag A star as it's called, right at the core of our galaxy. And this, I think, is very much an innovative way of observing. The center of the galaxy, of our galaxy, is enormously bright because so many stars are concentrated at its center. So it's a bit like looking directly at the sun. How can you see anything? Well, you can see things by taking repeated pictures of what's there, and anything moving at high speed will change its brightness slightly. So by subtracting one image from the other, you can see motion of objects right at the core of the galaxy. Incredibly innovative, and it works. And so these pictures are inferences of what's seen. There are lots of objects undergoing highly elliptical orbits, this one especially, this one here, about some very, very dense object at the center of our galaxy. We know of nothing else it could be except a black hole of about 4 million solar masses, as we could infer from Keplerian law. Why isn't this moving? There we go. Here's what gravitational lensing looks like. As I said earlier, you have some heavy object warping space around it. Here's the source of light. The light will cause it to lens as it goes to the observer. So the observer will think there's something over here and something identical over there, because our eyes, our observing instruments, would naturally infer the objects to be here if you didn't know there was a lens. It's a bit like the universe is sort of a funhouse mirror. You ever been in a funhouse, right? You have those curvy mirrors, they make you thin, they make you fat. It's kind of like God's played with the universe, kind of like that. You know? LIGO, gravity waves. Here's the, I think this is the one in Washington State. This is the center of the facility, and one constructs interferometers that are 4 kilometers long, and you send light down one end, down the other, and if a gravity wave goes by, gravity waves stretch space and time such that if one comes towards you like this, it has a quadrupolar oscillation. An electric field coming towards you like this has a dipolar oscillation, like so or like so. But a gravity wave coming towards you does this, or the orthogonal polarization like so. And what those polarizations do is literally stretch space in one direction and crush it in the other, and then vice versa. And so that warpage, it's very, very tiny. It's about a trillionth the radius, it's about a billionth the radius of a proton, 10 to the minus 21 centimeters. But that's enough to create an interference effect between the photons going this way and the photons going that way. And enough theoretical work has been done on what happens to gravity wave patterns in colliding black holes that you can compare the interference pattern to a template. And furthermore, there's a device in Washington, an identical one in the state of Louisiana in the United States. And if they both see the same template stretched out over the gravity wave travel time between the two locations, that's pretty good evidence you've seen something, and that's what was seen September 15th of 2015 and announced in February of 2016, and that's a picture of the patterns that they saw. A bit hard to see there. The bottom one is in Livingston, Louisiana. The top one is in Hanford, Washington. But that was, it's a gold-plated event, statistically verified to be there by chance to 1 part in 10 million or something. So finally, the Event Horizon Telescope is supposed to image a black hole, as I described already, so I don't think I need to say anything more on that. So I want to move into the subject of interest. There's still a lot of current research on black holes, which is a good thing because it keeps people like us all employed. At least I like to think that's a good thing. And I think we still have a lot to learn about them. There are still problems in classical physics connected with cosmic censorship and Nohair theorems. And there's actually quite an industry going on about finding solutions to equations numerically that have scalar hair. And we're learning things about black holes in that way. Quantum gravity. Well, this is still an unsolved problem. We do not know how to connect Einstein's theory of general relativity with quantum physics in any way at all. We don't even know if it must be done, though conventional wisdom says gravity should be quantizable the way electromagnetism and the strong and weak forces are. This subject is indirectly connected with that because the behavior of black holes as thermodynamic objects must have implications for quantum gravity. And one of the things I think that is an implication of black hole chemistry, as we'll see throughout this set of talks, is that we find a lot of new phenomena that are going to have to be describable by some underlying quantum statistical theory at the least, and it's going to be a lot more complicated than what you'll get for a Schwarzschild black hole. But we'll get to that as time goes on. In string theory, the ADS-CFT correspondence has indicated that a black hole in a space-time that is asymptotically negative curvature, what we call an anti-de Sitter space, a space of constant negative curvature, appears to be dual to a quantum conformal field theory at finite temperature, where the temperature of the field theory is the temperature of the black hole. And there's lots of stuff connected with that people are working on. People are constructing all kinds of exotic black holes, way, way different from when Schwarzschild about 100 years ago found one solution with painful effort. Now we have lots of ways of finding this. Thousands of people can now find black hole solutions. That's a remarkable achievement in scientific education, if you think about it. When Eddington was asked about general relativity by a reporter, I think this is either just before the bending of light discovery or just afterward, he said, somebody said, "Professor Eddington, I understand there are only 3 people in the world who understand general relativity." He said, and he paused and said, "Well, really, I can't think of who the 3rd person is." Presumably only he and Einstein did. Schwarzschild died. And finally, we have the observational aspects that I've talked about. So we have black holes that rotate, black rings, black Saturns, black strings, black sheets, black, 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 black. Lots of black. Right? So, any questions so far? All right. So let's do some basics of black holes to set up black hole chemistry. I want to start with Einstein's equations. And the way I like to think about these things is like any other equations of physics. The object of the game is, given some input to the equations with boundary conditions, what is the metric? So from a pragmatic viewpoint, the Einstein tensor is basically a set of differential equations that, if you solve them, tell you what the metric is. The stress energy is the input to the equations. You give me a hunk of matter, like a ball of dust, a star, or a distribution of galaxies, or something spinning, or whatever it is. You put that into this equations, find G, and then you're done. You know what the space-time is. Now, it's actually not really all quite that simple, but at a first level, it's just like electromagnetism. Maxwell's equations with a charge density, you tell me where the charge is in the current, you solve Maxwell's equations, you know the electromagnetic field. How tough can it be? So, I'm going to give an example of perhaps the most famous and useful solution that's come out in the last 50 some odd years. I'm going to assume there's axial symmetry. Going to be a little more complicated than usual. I'm going to assume there's symmetry about an axis like this, the z-axis perhaps, and I'm going to use what is called the electrovacuum. In other words, the stress energy is given by this object, which is the stress energy due to an electromagnetic field. So I'm not going to go through and solve the equations for you, but I'm going to remind those of you that know, and encourage those of you that don't, to read, that the answer is given by this metric here, which again is like flat space, but more complicated. This is the time, this is the radial distance away from the origin, this is the polar angle, theta, from the axis of symmetry downward, and phi is the azimuthal angle, the angle about the axis of symmetry this way. And it's got a complicated structure. This is known as the Kerr-Newman solution, first obtained in 1967. Kerr obtained a solution without charge in 1963. If you look at his paper, it's not comprehensible in any easy way because he used rather obtuse mathematics techniques. But the paper that found the Kerr-Newman solution is much more readable, and I'd encourage you to take a look at it. And this quantity delta here is this function here and here that basically tells us things about the event horizon of this charged, rotating black hole. This is the electromagnetic field associated with this object, and this plus this solve both Einstein's equations and the associated Maxwell equations, which I did not write down here. How many have seen the Kerr-Newman solution before? Okay, not a few of you, not as many as I thought. Well, I'm going to simplify this for you a little bit on the next slide, just to orient you better. But I thought I would show this more complicated thing because it will play a role in black hole chemistry to follow. You'll be seeing this thing again. So let's look at this and break this into pieces. In particular, let's look at a special case where the Q is 0, there's no charge, and where A is 0. Well, then you get what I showed you about 15 or 20 minutes ago. You get the Schwarzschild solution. Sigma becomes r squared, delta becomes r squared minus 2mr. So you've got r squared here. You can take it down, divide this by r squared, and you get this factor here. This disappears, and you reduce down to this where d omega squared is given by what we call the spherical volume element. Now, how many people have seen this before? More. That's good. So what I want you to get is this is a more complicated version of this metric when you have charge and rotation. So let's turn on the charge. Let's just set A equals 0. So now again, when A is 0, this thing vanishes, that one vanishes, this goes away, but this does not go away, and you get a more complicated version of this metric. It's still spherically symmetric, but notice the charge contributes with the opposite sign to the mass. And the electromagnetic potential is Coulomb's potential. So this would be what might result if you had a ball of matter collapsing about some net charge. Now that would be very unusual astrophysically. It's not impossible, but it would not be common. However, mathematically, there's no obstruction to it occurring. And so what I like to think of, we believe that this metric and this metric could describe situations in our real world. Now, they wouldn't be exact because there'd be other matter in the area curving space-time itself, but if these objects were isolated enough, they would be very good approximations to the curvature of space and time in their vicinity. And space and time really would be described by these things. In fact, we know from experiment this describes pretty well the metric of the sun. In fact, a better description of the metric of the sun is when Q is 0, but A is not 0. That's called the Kerr metric, or the Kerr solution. And the sun is rotating, and the Kerr metric approximately describes the curvature of space and time outside of the sun. It's not exact because if you have actually a body with mass that is not a black hole, then the Kerr metric gets a bit distorted. But still, if the value of A is tiny, then this works reasonably well even for the sun. So, usually people start with this, go to this, go to this. I started with the hard thing and showed you how it breaks up into pieces. So, any questions about this one?
How much is A for the sun?
It's very, I can't remember the numerical value. The angular momentum, we'll get to that in a minute. The angular momentum of the object with this metric is the mass times A, and that in gravitational units is, I think, on the order of 1% of the mass of the sun. But I can't remember the exact number right now. It's tiny. So in fact, you can approximate this, and the approximate metric is called the Lenz-Thirring metric. And it describes rotation. It describes the metric of a rotating massive object and it does allow you to see things like geodetic precession, namely if you have a spinning object and it's orbiting a heavy thing, its spin will precess due to the rotation of the other object, and that's what gravity probe B was supposed to measure, but unfortunately due to errors the measurement was somewhat compromised. Okay, any other questions about this? Okay, so in understanding these objects, a very useful tool is called a killing vector. In other words, we have these metrics. I mentioned the Nohair Theorem, that only a few quantities actually describe these. How do we connect these together? Well, the answer is via conserved quantities, and to do so we need something called a killing vector. Now, this is named after a man whose name was, believe it or not, Wilhelm Killing, a German. I always thought it was because it annihilated or killed something, but it's really the name of a guy. And he came up mathematically with this kind of quantity in the context of curved space, and we've now adopted it to curved space-time. And basically, it is a vector, xi, that obeys this equation here. And there's a more sophisticated mathematical way of describing it, insofar as you could say that if the metric has an isometry and you drag it, it stays the same under the isometry. But in practical terms, this is what you get. So the grad means the covariant derivative with respect to the metric of space-time. The simplest way of finding such things is to say if you have a metric and none of the metric functions depend on one of the coordinates, then there will be a killing vector associated with that coordinate. So for example, if the metric is time independent, then there will be a killing vector pointing in the direction of time. And that tells you the metric is static, or perhaps stationary. It tells you the metric looks the same tomorrow as it did yesterday. It doesn't change with time. There is, if you take the divergence of this equation, then you find you get this relationship here. This is, the first term gives you that, but this term, when you commute the covariant derivatives, ends up giving you this term, where that's the Ricci tensor. And so all killing vectors obey this relationship here, and that's going to be useful in what I have to say later on. In particular, in constructing what is called a conserved colmar quantity, which in differential geometric language looks like that. It's the integral of the dual of the wedge of d xi over some sphere, but that's a bit more awkward. So basically, you take grad A of xi b and then integrate it over some surface of interest, where the surface, because we're in a four-dimensional space-time, for example, has two normal vectors. If you think of like a sphere, it'll have a normal vector in space, but also a normal vector in time, for example. And if you carry out this integral, if a killing vector exists, then this object Q is conserved, associated with that killing vector. I'll give you examples right now. So what you can imagine is the following. Suppose you have some hypersurface here, and I want to think of a region within that hypersurface, and its region is bounded, let's say, by this. The hypersurface has a normal vector u. In other words, this is space at an instant of time. And everywhere on this surface, you have a normal vector, a unit normal, denoted by this quantity u. So that's one of the normal vectors. But now I want a surface within the space. So our room is three-dimensional. I can imagine, well, the surface of this table, for example. Here's a two-dimensional surface within our three-dimensional room. If I wanted to close it off, I'd have to bend the table around and so on. You get the idea. So that's what this surface here is, ST. There will be a volume in here. I might decide that this surface is hollow, like a hollow sphere. So there will be an outer boundary and an inner boundary, denoted like so. And this surface will have some normal vector that I've called S. So this surface element here will be given by the actual, what you would consider, if it were a sphere, you'd integrate over d theta sine theta d phi, and the normal vectors would be the radial vector and the time-length vector here. And so dSAB is given by this structure here, where this is the determinant of this thing right along this surface. So, now I'm going to apply this identity to this equation right here. And when you do that, you find that this quantity here is converted by this relation to this product of RAB with UA and Xi B. You end up, when you integrate by parts, getting this divergence, which is converted into that. And then by Einstein's equations, remember GAB is the stress energy, RAB is this combination of stress energies over this volume. So I'm converting this surface integral into a volume via Gauss's theorem. That volume gives you the divergence of this. That divergence is converted with this by this equation to give me this structure here. And I end up getting this right here. Of course, because of Gauss's theorem, if I'm integrating only over the outer surface, by Gauss's theorem I get the volume integral plus the surface integral over the inner surface, so that's what that quantity is right there. It's the Q associated with the inner surface. Now, what I want you to learn from this exercise is the Q on the outer surface is equal to the Q on the inner surface plus this volume integral. But if the stress energy is 0, if T is 0, this volume integral goes away, and the value of Q on the inner surface is equal to the value of Q on the outer surface, and that is what I mean by conservation. The charge doesn't care what surface you integrate over as long as the stress energy vanishes, or, before I get to the question, I don't even need T to vanish, all I need is for this to vanish. Yeah?
But that is given by the equation of the field equation.
Yes, to go from here to here I need the field.
No, I think the other side.
What other
The
side?
other one. Because...
This?
Okay,
I'm not, what are you referring to?
The other cube. You have
This here.
That. Yes.
No, well, no, this Q is associated, this is an H with that, this is an S with that. So I'm saying, I'm defining a quantity that is the integral over this surface here, outer. And then what I'm using is I'm using Gauss's theorem that the integral over a surface of a quantity is the volume integral of its divergence. I then take the divergence of this, which gives me that. I use this equation, which comes from here, to give me that. And then I use the Einstein equations to give me that. That's what I'm doing. Is that okay?
No.
I'm not sure what...
No, I have another question. Because you can think that the field equations are conserved by the Yankee identity.
That's correct.
So you can construct a current like, I don't know, the rich tensor plus the other thing.
Yeah, but I haven't used that here. You're right, but I did not use that in getting this. That's not the point.
Okay.
But you're right, you could do it. That, I'm not doing that. This is why, this is a different notion of conserved charge that plays a role in black hole chemistry. There's a relationship between them, but at the moment I'm just doing this. But you're quite right. The divergence of the Einstein tensor is identically 0. It vanishes for all metrics. Therefore, the divergence, the covariant divergence of the stress energy is 0. And if you integrate that over a killing vector, you get another notion of conserved charge, which is related to this but not identical.
And that doesn't mean this energy.
No, it doesn't. The point I'm trying to make here is that conservation, the notion of conservation here is this: you get the same answer for S as you do for H, provided there's no stress energy in the way. That's the point of this slide. Okay? So if you have a time-like killing vector, if Xi points in the time direction, or if it's d by dt, then we call this quantity the mass, And if xi is an azimuthal killing vector, let's say we had axial symmetry, which means we have a symmetry in this direction, which I'll call phi, then we call the conserved quantity angular momentum. And there are other conserved quantities one might construct as one likes. You might have translation invariance in one direction, in which case we call the conserved quantity.
Actually, you get J over 2, right?
Sorry?
So there is this problem with the colmar.
That is not the mass, it's a
There is a problem with the colmar definition of the angular momentum.
Yes.
So if you get the mass, then you get half of the angular momentum.
But it's okay. In ABS it's actually divergent, right?
Pardon me?
The colmar mass in ABS space-time.
Well, I'll get to the divergences, yes. So you've got to watch it. But this actually will work for BHC. And you do find this J is okay. But let me, no, I didn't animate all my slides. Let me just go ahead and flash these up. So for the Kerr-Newman black hole, you can calculate these things. And the total mass turns out to be this mass m. If I set g and c squared to 1, then in 4-dimensional space-time, this total mass is that mass, and it's the same as you would get from the other method. The angular momentum does work out to be ma, and in terms of the event horizon, r plus, where r plus, I didn't define it on the slide, r plus is the value of r that gives delta equals 0. So you could write m in terms of r plus and a, and this m is the conserved mass. M times a is the conserved j, and you get this. So here's I is d by dt, here's I is d by d phi. The asymptotic charge is given by this integral over the dual of the field strength. Basically, it's the integral of the field strength over a 2-dimensional surface. That turns out to be this little q. The event, oh, here's the event horizon here. I did have it, it's just in a different place. Delta equals 0 defines r plus and r minus. Whenever you have charge or rotation, in general, you find that there are 2 horizons. There's an outer one that distant observers at infinity all the way into the horizon experience time to the t coordinate to be a time coordinate. Once you cross through the surface, t becomes a space-like coordinate, but when you cross through the second surface, it becomes time-like again. So r minus is called the inner horizon. I'm not sure why that word's there. I think that's a mistake. The surface gravity of a black hole is defined to be, if you take xi to be the killing vector at the event horizon, which is actually, that generates the event horizon, as we call it. It's a linear combination of this one with that one. And then you take its gradient and then dot it into the killing vector, compute it at the horizon. You end up getting this quantity here, and that's what we call the surface gravity at the event horizon, or the surface gravity of the black hole. And the black hole, it turns out, this black hole has a surface area that is given by 4 pi times r plus squared plus a squared. And so these are the basic properties, the conserved q, m, and j, the conserved charges of the hole, its surface gravity, and its surface area. And I showed this more complicated example to show you that there is some interesting structure here, but hopefully not too complicated to look at. Now this area has an interesting property. It never decreases. And I want to say a little bit about that before I finish off. How am I doing time-wise?
Oh, it's okay. Half an hour.
Okay. So now we finally get to black holes as thermodynamic objects. And this whole notion started when John Wheeler was having a meeting with a group of his grad students. And he asked the question, what happens if you pour a cup of tea into a black hole? So I like tea. This is my tea, a little bit left, but it's stone cold now. He says, what if you pour this into a black hole? Remember, black holes are fairly new in the early 1970s. They were known to be hairless objects. They had no structure. They had only mass or charge or angular momentum. They absorb everything. They were presumably zero temperature objects with practically no structure. What if you poured a cup of tea into one? There you go. Well, the problem was this. The tea is hot. It has entropy. But the black hole is hairless. So how could it be any more disordered than it already was? It would gain in mass, but it surely could not gain any entropy. It absorbs everything. So where does the entropy go? Now, a lot of students thought, I don't want to do this stupid problem. But one of them, Jacob Bekenstein, thought, yeah, this is a bit curious. I'm going to work on this. And his thought was this: the T has mass, so the black hole's got to get heavier. But if the mass is bigger, the area gets bigger. Well, entropy always gets bigger in any thermodynamic process, or rather it never gets smaller. So maybe the increase in area is connected with the increase in entropy of the black hole. And that was published in this paper here in 1973. This notion that somehow area was related to the entropy of a black hole. That a black hole could be a thermodynamic object of sorts. Now, of course, this seemed kind of nuts because there's no temperature. How could a black hole possibly be hot? Anything that's hot has to radiate some kind of particles. If you burn wood, it radiates heat, infrared photons, light radiating visible photons. If a black hole has entropy, how is this possible if it has no temperature? Well, that's where Stephen Hawking came in, and I'm told he first didn't believe what Bekenstein said, but then on the order of a year later, he found that if you included quantum effects semi-classically, in other words, if you added quantum matter into the picture but kept the black hole classical, that black holes could indeed radiate heat. And he found that the temperature was equal to the surface gravity over the black hole divided by 2 pi, and the entropy was quantifiably given by 1/4 of the value of the area of the horizon, actually divided by 4g h bar to get the units right, and this h bar in front of it. So if Planck's constant vanishes, there's no temperature and it doesn't make sense. But if Planck's constant is non-zero, then you actually can get a temperature for the black hole. So this idea was quite radical at the time, but it led to the birth of black hole thermodynamics. It has a lot of strange features that we are still trying to understand. So it sort of solved John Wheeler's problem, but created a whole bunch of others. But of course, that's good news, because without it, I might not have a job. And maybe some of you too. There's a recent paper by a guy named David Wallace who gives a good overview of this subject. It came out on the archive last month. And he points out there are actually 5 ways of showing this. The first way was the hard way, using what are called Bogoliubov transformations in quantum field theory. Basically, what Hawking did was look at a collapsing object and found the relationship between creation and annihilation operators of a photon or some massless particle coming in from the distant past as the whole collapsed. It would be scattered off the whole. Part of the quanta would be scattered to the future, the other would go in the whole. And he found the Bogoliubov relationships between the creation and annihilation operators in the distant future relative to those of the distant past, and discovered that the only way they were consistent is if the spectrum of particles coming out was thermal. Then he and Hartle developed path integral techniques from Euclidean quantum field theory that were 20 times easier than this original way, and that's the way basically everybody uses today to calculate the temperature, but they are connected with this. A third approach that came out about 15 years ago, originated by Perike and Wilczek, and that Van Zo and Zerbini worked on, and that actually I worked on, developed with Ryan Kerner, is the tunneling approach. I'll say something about that in a minute. Then there's another approach in which you demand that the semi-classical Einstein equations in the exterior of the black hole have a consistent solution, and if you do, you find you must get a quantum state. And then finally, there's another approach by Wilczek in which you can demand that there be no anomalous breaking of diffeomorphism symmetry at the event horizon, and if you do that, you find the black hole has to have a temperature. But the most common ones, the popular ones, are these two, because they're the easiest to calculate with. There is a puzzle connected with these called the information paradox, and I'll get to that in a moment. So before I do, Hawking actually, I think in his original Scientific American article in the 70s, mentions this, but he never actually shows how to calculate with it. The idea is that quantum effects permit particles to tunnel out of the gravitational potential well of the black hole. Classically, as John Michell pointed out, this is impossible. And as we've seen from the Schwarzschild solution, to escape from a black hole, you'd have to go faster than the speed of light. But a quantum particle could perhaps tunnel, moving a little bit faster than the speed of light, but so quickly that the uncertainty principle washes out any possibility of directly observing them. So the idea is kind of like this. If you send an electron and have a repulsive negative electric field as a barrier, classically it'll bounce off. But we all know, or at least I think have heard of, that quantum mechanically, an electron can actually tunnel through such a barrier with some finite probability. And this is now the basis for all electronic gizmos like this one and my computer and so on. All transistors are based on exploiting this property in various ways using gates and drains and so on. Well, what about a black hole? Here's the black hole, and one way of visualizing how this can happen is that in quantum field theory, particle-antiparticle pairs, pairs of quanta and antiquanta, are created and destroyed all the time in empty space. And in particle physics experiments, we need to take account of this in a procedure called renormalization. So presumably this happens outside the black hole. Now and then, a pair might be created and get absorbed into the black hole. Most of the time, they happen outside, but very rarely, when a pair is created, only one goes in, and the other can fly off to infinity. And when that happens, a distant observer will see, oh, the black hole emitted something. Well, the only way that can happen by energy conservation is that the positive energy that an observer out here sees is taken away from the energy of the black hole, which means its mass gets smaller, its area gets smaller. So quantum particles tunnel out of the horizon. Now, as I said, Hawking presented this idea in his original paper, but it was only really these guys about, well, 17 years ago now that quantified it. People didn't do much with it, and then these papers here show that this is very broadly applicable to all kinds of particles, spin 0, spin 1/2, spin 1, all kinds of black holes. And this started a bit of industry where there's been lots and lots of papers written where everybody takes their favorite black hole, their favorite quantum field, applies this procedure and shows, hey, these quantum fields are radiated with the temperature of the black hole. So, again, it kept lots of people employed. The point is that a black hole is really a hot object. It effectively radiates particles due to this process that occurs in quantum field theory. So what about this information paradox? Well, Hawking noted this in 1976. As I say, the problem of what happens when you pour a cup of tea into a black hole is resolved by this, but it creates what some regard as an even worse problem, or better, depending on what you feel about physics employment, that we still don't know how to solve. And this process came up in the 70s, it died down, it emerged in the early 90s, it died down, it came up again about 5 years ago, it died down. It seems to go through waves in physics where lots of papers are written, everybody argues, nothing is solved, it goes dormant, and then the process repeats. So hopefully in another 15 years, all of you will experience the same thing. So what's the deal? Well, the deal is the following. Suppose here is a space-like surface outside, let me not put that up for a minute. Here's a space-like surface outside the black hole that later on becomes this other surface, and time evolves. Now the problem with a black hole is that it severely warps space and time. So here's a ball of collapsing matter, and before the singularity forms, so time is going this way, so here's a ball of stuff collapsing. At this point in time, you get a trapped region. In other words, if you're in this object here, you can still get out. It's not too late. But after this time, if you're here, you are doomed. You are going to get stuck in this thing. You will never get out. You'll crash into the singularity and die or be saved, or we don't know what will happen to you. But whatever happens to you, you're not getting out here. Okay? So, this is the inside of the trapped region. This is the outside. And if you have a virtual pair of quanta created, as I showed before, this one can escape to infinity, but the red one, its antiparticle partner, cannot escape. It's on this space-like surface. Later on, this quanta moves a little bit away. This quanta here moves into the hole. Everybody get the idea? That's what will happen over time. So now, if it's in a quantum state, we know from this process that the red and blue particles are entangled, like so. So this could be either in the state 0 or the state 1, and likewise for this. And so this is a possible entangled state of this quantum pair that will time evolve to this entangled state. But we also have the matter, which might be a complicated mess, but it will be inside the black hole. I'll represent it by phi. Maybe it's a single quantum state itself. Okay? Now, outside people have no way of knowing what's in here, so their quantum state is given by taking the trace over all the inner states. And we describe this in quantum physics by what is called a density matrix.
What is 0K? What is the meaning of 0K?
It means the ground state of this quanta that has a momentum k. So either this state could have a vacuum state of k or an excited state of k in this simplified picture. But you can think of it maybe as the particle-antiparticle are created with a low energy state or a higher energy state. The lower energy state is 0, the higher energy state of 1, and it has momentum k, and the other one will have momentum minus k. So the outer guy, I call the outer guy minus k, the inner guy k. So basically the pair's created, one goes that way, the other goes that way. I suppose I should have called the blue guy k and the red guy minus k, but I did it the other way around.
Why do you have two?
Why do I have two what?
Why you have 0K? So again, you have
this is a low energy state of this quantum pair. This is a high energy state of this quantum pair. So this guy's created in a low energy state with momentum minus k. The partner's created in the low energy state with momentum k. 0 means low energy.
Okay.
1 means they're in a slightly higher energy state.
But when you have this configuration, you have a...
Well, I could have put a minus. In general, I'll get to that in a minute. But in general, they are created in an entangled state that can look like this. And I haven't proven that from quantum field theory, but this is in fact what comes out when you look at quantum field theory near a black hole. If this happens far enough away from the collapsing matter, then this will not be entangled with that. And so that's why I have this extra part of the wave function out here. Now sorry?
So you say that there are two particles being created, one in a higher...
No, I'm saying there's a particle-antiparticle pair being created, momentum k, momentum minus k.
Okay, this is one.
No, that's either they will both be in the 0 state or they will both be in the 1 state.
Okay.
That's what I'm saying.
Okay.
Okay?
Okay.
And there will be a third quantum state of the matter that's a direct product with those two. That's the assumption that what's going on here is far enough away from that. If you look at the space-like distance, it turns out because of the warpage of space, this is an enormous distance inside the hole. So it's probably a good assumption that this has nothing to do with this entanglement. Okay? So then what I do is I'm an outside person, and I say, in order to understand the quantum state of this blue particle that I see, I have to trace over the inside. And the trace I get, I haven't done the calculation here. Those of you that are familiar with, how many are familiar with density matrices? Not many. Basically what I'm doing is I'm taking the expectation value, I'm taking this state and I'm taking its inner product with 0 of the inside, adding it to the inner product of 0 of the 1 with the inside, and that is an expression of my ignorance over what is on the inside. It could either be 0 or 1, I don't know which it'll be, so I take the inner product of this whole thing with 0 of the inside, add it to the inner product of the whole thing with 1 in the inside, normalize the state, and I get a matrix that looks like that, which you can see is half the identity matrix. And what that means is that this is coming out in a completely random thermal state. I have just as much probability of observing this guy to be 0 as I do of observing it to be 1. That's the take-home lesson from this. And because of that, this state has an entropy due to my ignorance here. It's given by this von Neumann formula, which means I take the logarithm of this matrix, multiply it by the matrix and trace, and if you're like me and are bugged by the logarithm of the matrix, diagonalize the matrix. The log of the matrix is the matrix of the log of the eigenvalues, and so this is a half log a half plus a half log a half with a minus sign, and so you end up getting 2 log 2. Sorry, log 2. That's an error. This is right. That's an arithmetic mistake. Sorry, log 2, not 2 log 2. My apologies. So, now there'll be, that's one emission of quanta means that that quantum that I see way out here has log 2 in entropy. So now, a little later on, another pair will be produced under similar circumstances. This will be the matter state a little bit later. So here's the first emission, here's the second emission. So now, if I take the trace, I have 4 possibilities, each one with probability 25%. So now I get twice as much as I had before, which is 2 log 2, not 4 log 2, but it's still double. And after the nth emission, I'll have a product of all of these things. I'll get this diagonal of 1 over 2 to the n in every matrix. I'll get 2 to the n log 2. And the point is, as the number of quanta are emitted, the entropy grows unboundedly. I get more and more disorder. This is a bit like a quantum version of the Nohair Theorem. I am unable to learn anything about what's going on inside the black hole. I just find I get this huge amount of entropy. But the problem is that the black hole is decreasing in mass, and what I see when the mass goes away is a whole bunch of particles that are entangled with nothing. But you can't be entangled with nothing. That makes no sense. And if you look actually at how many quanta are emitted, there's a numerical factor that's of order unity in this process, depending on the matter. This is the Planck mass here, that's the mass of the black hole. If you calculate the value of n that you would get for a realistic black hole, you get 10 to the 76. So the entropy is 2 to the 10 to the 76. This is a ridiculously large number, vastly larger than the entropy of anything else we know in physics. The entropy of the sun is 50 orders of magnitude smaller than this. So it's very strange. You've got a sun with an entropy of about, I don't know, 10 to the 30. If it collapsed to a black hole, all of a sudden its entropy would jump 50 orders of magnitude. This is not impossible, but it's certainly weird. So, furthermore, the bigger problem with this paradox is you've got whatever you would have structure in the matter collapsing to a black hole, and if you waited until it evaporated, you'd get a quantum state fully thermal entangled with nothing with an enormous amount of entropy, which means you've lost information. If the black hole really does disappear, then you have destroyed what in quantum physics is called unitarity, which unitarity means you have the ability to either predict the future from the past or retrodict the past from the future. You lose that second possibility if this process goes right to zero. That is what was called the information paradox. Whatever information was contained in the initial matter is ultimately gone. So, several solutions have been proposed to this problem over the years, and none of them are satisfactory. One is the process stops. Hawking's calculation was approximate, the black hole shrinks, but eventually it doesn't radiate forever, something turns off the process, and there's a hunk of junk left over that we call a remnant. Well, the problem with that, so that's this idea here. Something terminates the evolution before you get down to the Planck mass. Maybe only a little bit, nobody knows. Well, the problem is that we've got this huge amount of entropy out front, so that means the remnant has to contain this information that outside people don't see. You've got a very small object with an enormous number. Small means small not only in size, but also low energy. You've got a very low energy object with an enormous number of possible quantum states. We don't know of anything like that. To make matters worse, if it's too small, then even though it might have a very tiny coupling to ordinary matter, because there are so many kinds of them, you should have seen them in particle physics processes. So the idea is this. I could scatter an electron and a positron off each other. They might have a probability, if these remnants couple to ordinary matter, which they have to for the black hole to radiate, even if I make that coupling super tiny, you might say, okay, I've got a probability of 10 to the minus 80 of producing one of these remnants. The problem is I have 10 to the 80 different remnants. So by just the simple laws of S-matrix scattering, you're going to have 10 to the minus 80 for any one kind of remnant, but you have 10 to the 80 kinds of remnants. So you have a probability of order unity of producing these things in particle physics. Nobody's ever seen them. That's why people don't like remnants. The next thing, mixedness. The black hole evaporates with this entanglement entropy, but it leaves, it's unentangled with any quantum state. In other words, okay, you have a well-defined quantum state with information. Yeah, you lose the information. The final state is what we call a mixed state with less information. Now, everybody is happy with that solution in physics. except particle physicists, who hate it and think this is wrong. It violates unitarity. And this is the major disagreement, perhaps, within the community between those that believe unitarity should be preserved and those who think, well, what's the big deal? The big deal, one of the reasons for thinking it's a big deal to violate unitarity is this ADS-CFT correspondence. That it's not a proof, but there's suggestive evidence for it, that the black hole is dual to a quantum field theory. The quantum field theory obeys unitarity, so how could the black hole possibly violate it? However, Paul Davies has said, look, you go into a room of any other kind of physicist, you tell them unitarity is violated, they say, okay, yeah, so what, who cares? But you go to particle physicists and they'll freak out. So if we give this up, it shouldn't be done lightly. The third is bleaching. Information actually never gets in the black hole. And back in the 90s, I think Preskill called this bleaching. So suppose you throw an encyclopedia into a fire. Well, you'll lose the information of the encyclopedia, apparently, but not really. If you put enough photon detectors outside of the fire, collected every bit of the spectra that came out, in principle, you could reconstruct the encyclopedia. But if you threw one into a black hole and it radiated away, what I showed you before says no. That encyclopedia is gone forever. You cannot learn what was in it. But if it's bleached, then you can. But that's pretty weird. You throw the encyclopedia into the hole, and some mysterious force erases it. And that all the information is somehow, the mass of the encyclopedia goes in, but somehow its information bounces off and escapes. No one knows how to do this. And the problem with it is the initial state should never have formed the black hole in the first place. Or if it does, what is it that's repelling information? Well, this idea died down, but in my opinion, it was revived 5 years ago, and we now call this a firewall. There was a new reason for thinking there were firewalls. Basically, do I have time left to a short story, 2 minutes? Or?
10 minutes.
Okay, I'll do this, and then if there's any questions, I'll take them. So what came along after this was the early 1990s. Susskind, Uglum, and Thorlacius proposed a notion of black hole complementarity, which was basically we can have our cake and eat it too. The idea was outside people only see what's outside. Inside people can observe what's inside, and so he thought, let's preserve unitarity for the outside people. Well, if you do that, then what about this problem with the entropy? Well, the idea was that outside observers can make observations that are fundamentally contradictory with inside observers, but you can have both because the two can never talk to each other. Well, that idea was destroyed by this paper called the AMPS paper, Alhiri, Merrill, Polchinski, and Sully, who basically pointed out that if this idea is right, then you violate something called quantum monogamy, which basically says that this pair of particles, when they're pair-produced, they're maximally entangled in one of two possible states, such as what I showed with the zeros and ones. In order to realize that, you would have to violate a theorem in quantum mechanics that says that any two particles that are maximally entangled cannot be entangled with a third party. And so that destroyed the idea of complementarity, and they thought, well, to preserve unitarity, what we need to do is prevent this maximal entanglement. In other words, what we want is the stuff forming the black hole and the early quantum states after it's formed are not entangled with what goes inside. Instead, they're entangled with what comes out later on. And if that's true, then the junk going in, which has information about the hole, is entangled with the stuff much later on as it evaporates to nothing, and so you could reconstruct the information from late stuff relative to early. But then the question is, well, wait a minute, what about the part of the thing that fell into the hole? Well, the idea of a firewall is let's get rid of that by saying, instead of the edge of a black hole being a benign thing that you could fall into, is actually a highly violent, excited state that basically effectively destroys the other quanta going in and preserves entanglement between early and late. And that's the idea of the firewall. In other words, in a normal black hole that radiates, if you wanted to learn what was inside, you could jump into the hole, and you wouldn't get destroyed. Well, if it were a solar mass black hole, your guts would get ripped apart due to the different tidal forces, but it doesn't have to be a solar mass black hole. The bigger the black hole gets, the weaker the gravity is at its edge. It's possible to make a black hole large enough that the surface gravity is the surface gravity of the Earth. Well, I can jump into that. That's easy, right? I live. So if the surface gravity of the black hole were the same as here, I could jump in without a problem. But the firewall people would say, no, you can't. If you try that, you'll be burned up by this set of highly excited quanta that prevent the information that you are from getting in. Basically, you'll be burned to a crisp, and all the information that is you will get sent out to the rest of the world, just the way the encyclopedia's information gets sent out as it's burned in the fire.
But then the black hole can never increase their mass.
Well, that's the problem. I am not a fan of firewalls. I'm very skeptical of them.
No, but they can you explain the black hole that took us 10 million.
Well, that's the problem of those people, not me. But this paradox they pointed out relies on three things being true at once. Unitarity, which means you can predict the past from the future. The equivalence principle, which says at the edge of a black hole, you can always approximate space-time to be flat, and there's nothing excited. And, which I didn't talk about much, was local quantum field theory. The idea, I implicitly did it there, the idea that the physics of the entangled pair can be very much decoupled from the physics of the jump collapsing. One of those things has to be given up. If you give up the equivalence principle, you get a firewall, and I think you do have this problem. If you give up unitarity, then particle physicists will come to your house at night and put you in a pair of cement overshoes and take you to the beach at Vigna. And if you give up locality, well, some people do that. This is where the problem stands at this point in time. I'll stop here for now.